This recording is protected by copyright. No part may be reproduced without the prior permission of the University of South Australia.
Okay, this is the first 2 minutes are going to be bookkeeping really up. We missed Monday because a horse race is very important in this country. So because of a public holiday, we need to reschedule Monday's class, right? Now, for this class, it's important that the lecture comes before the tutorial. All right, so today we'll have a lecture that was going to happen on Monday. And next week, we're going to have a replacement of today's tutorial. All right? So that will occur next Tuesday. To 4, age 135. In that tutorial, we are going to have the quiz. Okay? Open book quiz. And it's a short thing, 15 minutes only. And hi. And whenever we have a problem on a Monday, if we do have another problem, we'll do the same. Okay. Today's topic, well, ultimately, today's topic is the derivative, all right? So we'll get there in little stages. I'm not going to tell you right now what was the historical motivation for derivative. I'm only going to tell you one of the motivations. It was not even the most important motivation. But it was important enough, and it's very easy to visualize. Okay? Here's what you go. You want to have a mathematical way of describing tangent lines to curves that you draw. So you draw a curve. It doesn't have to be any special curve, just any curve you draw. And you want to know what is, well, you want to know what is a tangent line. And once you have a notion of what the tangent line is, you want to know how can you compute the tangent line in some sort of mathematical way, or which is to say, through equations, right? Now, the truth is, okay, a tangent line is like art. I know it when I see it. Is it art, right? Is it art? I know it when I see it. So, not tangent, okay? Not tangent. Tangent. So if all you had to do is to look at a picture and tell me when it is tangent and when it isn't, I would expect that everybody would be able to do that. Do you understand what the notion is? Okay? If I were forced to describe it, I would go and say, all right, okay, you have your curve over there, or a bit of it. and you get a ruler or a straight edge or something long, thin, straight, okay? And you bring it outside here and you move it towards the curve until it touches, and then you stop. Just at the first point of contact, right? Tangent, ta-da. Now, you mind you that you can be tangent somewhere and not tangent elsewhere. That's all right. Okay? This red line here is tangent to the black curve at the tangency point. And then it cuts it across somewhere else, and you don't care about that. Okay? I'm not talking about somewhere else. I'm talking about close to the point where it touches. Okay? So if something like this happens, you say it's secant. Names, right? Secant. You could call it Bob if you want, but it's secant. That is a tangency point. If you stare at it long enough, let's say 100 years, stare at it for 100 years, you come to realize that the key point of what we said is that to detect a tangency point, you need to look only near the point. Far away, you don't care. And that's why we invented limits, which is stuff we talked about in the previous class, to be able to talk about things that happen near a point. Far away, you don't care. And the correct language to express mathematically the concept of tangent is the language of limits. Okay? All right. So let's see what people did. And this is before Newton. We say Newton and Leibniz invented calculus, which is true. But before Newton, people already kind of knew what to do. And here's what Fermat and Pascal already knew. Okay? I'm going to put the Cartesian x and y here, and I'm going to put the curve we had here on the axis as a graph of a function. All right? So we're going to look at tangent lines, but in the context of functions. So draw your function over there. I'm going to give it a name. And what they said was the following. Okay, all right. I'm going to pick a particular point, a spot on this curve over there. Let's say here. I want to draw a tangent line here. Okay? Now, if I adopt this mechanical way that I had before, what do? I get my straight edge, my wooden rod or whatever, okay? And I come outside here, and I go ooh, until I touch exactly at that red dot. Okay, if I touch somewhere else, I made a mistake. I had, do it again. Ooh, until you get exactly here, and when you touch that, that's the straight line. Okay? That's a bad way of doing it, turns out. Okay? There's a better way of doing it. The better way of doing it is this. Get your straight line to begin with, and make it go through this point. And not necessarily tangent. It could be a secant line. Doesn't matter. Okay? In fact, it's much easier to write it as a secant line than as a tangent line because there are so many secants, right? But there's only one tangent. So you draw it. Let's do it in blue. I'm going to draw this one here. It doesn't have to be this one. Okay? Now that's a secant. And in the picture I drew, you'll notice the following. It cuts the black line somewhere else as well. Okay? It cuts it here. Okay? Now that's not tangent. Not yet. This is not a tangent line. The blue line here is not a tangent line. Okay? It's a secant line here in the picture I drew. I mean, if I had by any chance drawn the tangent line, it would be such an incredible coincidence. It is not likely that I did it. Okay? That one is secant. Now I'm going to go back to my mechanistic mechanics, things that have movement, right? Mechanistic ways. But instead of getting my blue line from outside and touching on that point, here's how I'm going to move the line. I'm going to keep this point fixed, and I'm going to spin the line around. So you're allowed to spin the line about this point. Okay? And most of the lines, as I mentioned, they're going to be secant. Okay? They're going to cut this across and not tangent. All right? But take a look at what happens, and I'm going to draw here because I don't want to clutter that image. Take a look at what happens when you draw many lines. This line is wrong. It's not the line I want. Okay? This line is also wrong. But would you say it's better or worse? It's a judgment call. Morality in mathematics. Better or worse?
It's better.
It's better. It's better because, you know, if I'm looking at this, I'm thinking the tangent has to be here, and this one's kind of sloping better. Okay? And if you want to make it better still, keep in mind that the tangent line should be somewhere here, but I'm not drawing it. If you want to make it better still, you slope it a little more that way. Still not right. Okay? If you slope it too much, you went past it. Don't want to do that. All right? You want to do it just right. Okay? So you understand what the technical challenge is here. What these two guys realized is that to do it just right, you use the help of the black line itself, because there is this other point of contact here. Okay? So imagine, if you will, that you have a mechanical device where this is always fixed, and this is the guy you can move. I can move the blue dot along the black line. If I move the blue dot away to over here, if I move the blue dot away, this blue line becomes that line. And it's getting worse. But if I move the blue dot closer, Things are getting better. And closer, and closer, and closer, and closer. I do not want the blue line to coincide with the red. Oh, beg your pardon. The blue dot to coincide with the red dot. If they actually exactly coincide, you lose. I mean, it can spin out of control. So I want the blue dot to get as close as I can possibly make it to the red dot without actually being equal. And golly, if you remember last week, that's exactly what limits are all about. You want x to go to the value a, but being different from the value a. Remember that? I know it's a whole week, but okay. These two guys realize that. It may be even that other people realized it before them, and they were just building on what other people did. Okay? They actually computed the equation for a tangent line if the black curve is x squared. So they did it for the parabola. They knew how to do it. So Newton wasn't the first. Leibniz wasn't the first. Okay? So let's write all of this now in mathematical language. We're going to start putting symbols in here. Okay? Now, let's see. What we're looking for. Looking for a tangent line. There are two words of importance here. The first one I want to underline is line. There's a pun in there somewhere. Underline? Sorry. Okay? Forget about being tangent. Any line that I write, any line at all that I write, has an equation that looks like this. Y is equal to mx plus b, unless the line is vertical, but we're not talking about vertical lines here. So if I want to find, I want to find a tangent line, I want to find the number m and the number b. If I know these two numbers, I know the line. So that's the goal, m and b. And we're not going to find them at the same time. We're going to find m first, and then we're going to find b. Okay? It turns out that once you find m, it's very easy to find b. So the real difficulty is finding m. That is the trouble. Okay? That's the difficult one. If you know this, that one, very simple. So for all practical purposes, I'm going to forget about b. I'm going to concentrate on the m. The value m for any straight line is what we call the slope of a line. So let me spend 2 minutes talking about the slope for a straight line. So the equation here is y equals mx plus b. And if you want to be more concrete, you can think of it as that one. It doesn't do you any harm. Okay? And I want to concentrate on the slope. What does the slope m means? Well, let's see. It does mean the following. Go anywhere you want, here, and then move 1 unit to the right. So this is 1 unit. So you have a horizontal displacement of 1. Check out your vertical displacement. So we move that to the line, and check out the vertical displacement. This is 1. This is the vertical displacement. The vertical displacement is the quantity m. Okay? That's what this m means. So in this equation, in this straight line here, if you change your x by 1, your y is going to change by 2. Okay? You can check that by doing the following. I'm going to call this guy here a. So this is a plus 1. I'm going to compute the height for a, which is going to be this value here that I'm going to call y0. So in this line here, y0 is 2a plus 3. I'm going to compute this height here, which I am going to call y1. And y1 is the height I obtain when I replace x by a plus 1. And I want to figure out the displacement in the vertical, which is y1 take away y0. If I do y1 take away y0, you have 2a plus 1 plus 3 take away 2a plus 3. You notice that the 3's cancel, and the 2a's cancel. You're left with 2. All right? So as promised, if you have a vertical, beg your pardon, if you have a horizontal displacement of 1, you have a vertical displacement of m. You can redo this that I have here in red for that one in there, substituting m and b for 2 and 3. Okay? I never really used the fact that it was 2 and 3, so you can write m and b, the same stuff, and you're going to get m in the end. Okay? So that's the meaning of a slope. All right? Now, physically, let's put some reality back into the mathematics, as real as we can make it, okay? Let's say that x corresponds to time, and y corresponds to distance traveled, okay? Let's say you are traveling at a constant velocity. What's your velocity? 2 meters per second. Now, 2 meters per second is too fast for me. I'm an old guy, okay? But let's try. You're not taping that, are you? Okay, let's see. George goes to the Olympics. 2 meters per second. Now, what's 2 meters? 2 meters is over there, right? 1, 2, 3, 4, 5. Okay, 2 meters per second. Constant speed. All right? Constant speed. I have to keep 2 meters per second. Okay? So x is time. It's seconds. After 1 second goes by, I travel 2 meters. And it doesn't matter where I measure the 1 second. I can measure the 1 second right now, and I travel 2 meters. And I can measure the 1 second much later, and I will still be traveling 2 meters because I have constant speed. Right? And if I had to graph the distance I traveled with the time it takes, it would be a straight line graph. And if at time 0, x equals 0, I started 3 meters from the start, because, I had to have a head advantage over whoever is behind me because I'm an old guy, right? Okay? Then it's exactly this equation. Did you see that Prince, what's his name, was racing against Usain Bolt? Yeah, well, he won. Right. Okay? All right? So that's the meaning of a slope. That's the meaning of a slope. How do you compute the slope? How do you compute the slope? Well, there are ways to compute the slope. Okay? Right? I mean, if you know the equation of a line, you don't need to compute the slope. It's already there. It's that number that's multiplying the x. But let's pretend that we don't know the equation of a line, but we have a detector that can tell me where 2 points on the line are, right? How do you compute the slope? Well, let's see. What that is telling me is that if I pick any value a, and I go one more, okay, and then I measure the corresponding heights, then the slope is going to be this height here, which is y1 minus y0. Okay? All right? So that gives me a way of computing the slope if by some weird reason I do not have the equation, but I know the coordinates of 2 points on the line. Moreover, on the horizontal, they have to be 1 apart. Okay? All right? So it's a very, very specific way of computing slope. Now, what happens if they are not 1 apart? What happens if they are age apart? Now, I'm going to leave the +1 there. I'm sorry. What happens if they are age apart? You use similarity of triangles here. Okay? Here you have y0. Here you have. Do you mind if I still call it y1? No, let me call it y age. Y age. There is a triangle here. Okay? I cannot say that the slope is this difference because this is not 1 now. But compared to that picture, okay, and use similarity of triangles. This is the slope. M divided by 1 is equal to this height here divided by this distance here, which is h, right? And this height here is yh, take away y0. So let me write that down. Okay? It's what we call rise over run in English. When I grew up, I didn't know that because I didn't learn it in English. I learned it in Portuguese. But rise over run. Rise over run. Okay? We also call it, if you want, delta y over delta x. Now, delta is a Greek letter that we use in mathematics to represent a difference. Okay? So what it says is the difference of the y values, the difference between the heights, divided by the difference between the x values. These are the two x values in consideration. The difference between them is age. All right? Let there be light again. So far, I want to make sure that, this is for a straight line. So now let's put this picture here, rather this picture here, in the other picture when we want to find the slope of a tangent line. This is for any line. Now let's get to the word tangent in it. Okay? All right, I'm going to fix here a position A in the x-axis. And once I fix that one, the height is fixed. I used blue before, I used red before, so I'm going to use red again. Okay? And what is this height? This height is what in there I called y naught, but in here I'm going to call f of a. All right? Now I'm going to choose another point in here. Not necessarily at distance 1, at distance h, a plus h. So this distance here is h. And when I move that to over there, I have the blue point, the blue dot. It's better if it's straight, isn't it? All right? So there's the blue dot. And there is a secant line that I'm going to draw very, very, very faintly here. Over there. And this height here which in the other picture I called YH, it is f of a plus h. Okay? Example. Y equals f of x is equal to x squared. The example that Fermat and Pascal did. Okay? I'm going to pick a value. I'm going to pick a value for A. Seven. Yeah, people have the strangest tastes, you know, in number. What's wrong with 1? Anyway, 7. All right, okay. I don't want to be too critical. 7. So the picture, if you want to draw a picture of that, that's the picture of a parabola. A parabola looks like this. Okay? I will necessarily have to draw it off scale because 7 is, if I put 7 here, I have to put 7 square, 49 over there. I'm going to go off the wall. So I'm going to pretend this is 7, and that is 49. Okay? All right? So what we're saying here is that 49 is the value y0 is f of 7. Okay? You with me? And if I go a little further than 7, to 7 plus age, and I do not want to put a value for age because that is the whole point here, okay? Not plugging in a value for age. That age is going to be a sliding variable. I want to make that quantity small because I want to slide the blue dot to the red dot. Okay? Then I'm going to have another height in there. That is going to be my other height. It's the height y age, which is f of a plus age. Now, what's f? F of anything I put in there squares that thing. Okay? If you want, you can think of f of box is box squared. Whatever is in the place of box. In here, I have a plus age. So you have to do a plus age and square it. So that's a squared plus 2a age plus age squared. But a is 49. A is 7. So this is 49 plus 14 age plus age squared. And that is what comes in here. So I'm going to use a different color, otherwise it will be a bit difficult to see, but this height here is 49 plus 14 age plus age squared. Now, if you plug in a value of age, you get a number there. Okay? So if age is 1, this is going to be 49 plus 14 plus 1. 50 plus 14, 64. All right? And if you plug in a value age equal 0.05, you get a number, etc., etc. We're not going to plug in a value of age. What we're going to do now is compute the slope of the blue line. Take a look at what's written here on top. The slope of a blue line, the m for the blue line, is the difference between the ages divided by, sorry, I beg your pardon, the difference between the y's divided by age. And so I'm using this formula here. Check it out. Check it out. What does it have to be? Y age. and y age is f of a plus h, take away fa, which is y0. Take away y0, which is f of a. That's the slope of the secant line. So let's write that in bright red. All right? That's the slope of a secant line. And now that you have a formula for the slope of a secant line, how do you get the tangent slope? Yeah.
Add a limit.
You do a limit, okay? You want the blue dot to slide towards the red dot without ever getting there. So you want it to be as close as possible without getting there. That's a limit. But I'm not going to write limit when the blue dot does that, because that is kind of silly, okay? You're going to write it in terms of the value of age, because the blue dot sliding down to the red dot is the same thing as getting the value of age smaller and smaller and smaller, but never 0. And that's the fundamental insight, okay? That will allow you to actually compute these things. So the slope of a tangent line now, I'm going to write here at the bottom. The slope of the tangent line is given by the limit when the value of age goes to 0 of that quotient. I'm going to give this a new name and a symbol later on in the second half of a course, of a class today, but let's compute it in this case here. Now, I'm going to do something that's very symbolic. I'm going to erase the picture. Okay? I'm going to erase the picture. I'll tell you why this is more important than you know later. I have an option here. I can erase the equations or erase the picture because I run out of room, right? I'm keeping the equations and erasing the picture. That should tell you something. So let's see. I want to compute, first thing, this. I want to compute f of a plus age, take away f of a, and then I want to divide by age. And what is that? Well, check it out. F of a plus age is equal to this. We've done the work. Okay? If I'm ever in front of a, let me know. 49 plus 14 age plus age squared. Take away f of a. F of a is 49. So take away 49. Divided by age. Now what do I want to do? I want to take a limit when age goes to 0, right? Now, remember what we talked about last week the first thing you do when you have to take a limit is to actually plug in that value of age and see what happens. Okay? So what happens if you plug in age equals 0 in this fraction here? You get 49 plus 0 minus 49, 0, divided by 0. 0 divided by 0 is bad news for you and me and everybody. It could get you anything. So you need to simplify this so that it is not looking like 0 divided by 0 anymore. Okay? Take a look and see if you can simplify. Oh, look, I am so lucky. 49 take away 49 is 0, so simplify. This is 14h plus h squared on h. Can I simplify further? Because this is still 0 divided by 0. If I plug in h equals 0, it's 0 plus 0 on 0. 0 on 0? No. But you can simplify further. This is 14h divided by h plus h squared divided by h. Now simplify. This is 14 plus h. Why can you simplify? Because if you remember the limit, the age gets close to 0, but it's never equal to 0. And if it is not equal to 0, you can cancel these guys. So there you go. It's 14 plus age. Now, if you substitute age by 0, you get some. You don't get 0 divided by 0 anymore. Okay? And the conclusion is that in the example, the limit when h goes to 0 of f of a plus h minus f of a divided by h, it's 14, a number. Okay? What's the meaning of that? We went through all of that and maybe we forgot what we were doing. The meaning of that is the following. If I am going to write the equation of a tangent line, the equation is going to start y equals 14x plus b. I just found that the number that goes in there is 14. And the b is going to be easy to find. I'm not going to bother with it right now. We're going to postpone that discussion until later. But really, it's not a concern. The important and the hard guy to get is that 14 over there. Yeah?
Is that tangent the instantaneous rate of change?
The tangent line is not the instantaneous rate of change. But the number 14 is the instantaneous rate of change. We'll talk about that when you see me run my course, but not with a constant speed. Okay? So there's a lot more interesting physical comedy coming. Let's take 10 minutes.